All right, so linked lists. This is a foundational topic in software and computer science. Um, it's not like you'll ever really, well, you certainly won't ever be implementing a linked list in a job, but you also won't be using linked lists very often, to be honest, depending on what work you're doing. Um, Most programming languages have discouraged linked lists for a long time. If you just reach for a generic list, like I just need to store some elements in some linear order that doesn't change around on me. If you reach for that sort of off-the-shelf like solution in a programming language, you're usually not going to get a linked list. And I mean, the first thing I think of is C++, where the sort of go-to data structure is standard vector, which is an array that just is a dynamic array, which means that once it gets too big and you try to add another element to the end of it or somewhere in the middle of it, and it runs out of space, then it just copies to a new array that is larger that can accommodate it. But it's just an array. Java is the same idea, array list. It's a dynamic resizing array. I mean, Scala, the default sequence data structure for mutable sequences used to be this funky trie data structure that did some magic, but nowadays it's just like Java. It's an array list basically. The immutable data structure by default is a linked list, though, and this is Scala's functional roots, because linked lists are actually still used in your functional programming languages all the time. If you're using Scheme or something, then it's the most natural thing in the world to just construct a linked list. And you kind of need to know about that. Oh, Golang also is like your go-to data structure. Really the only one that you can use is slices, which are nowadays at least just dynamic arrays. So you won't often be using linked lists. But more importantly, linked lists are a foundational topic. It's something you need to know. If you're going to be implementing, like, for example, a spatial data structure, a KD tree or a quad tree or something, or an oct tree, or maybe blockchain stuff, then it's helpful to have this like very simple linear data structure in your back pocket as like knowledge that you know, because the same concepts will apply, and it's good to have the simpler stuff down pat first. Let's get started. The point of linked lists, the thing they're good at, is operations at the head. So we have our diagram here. The first element in the list is called the head. The rest of it is the tail. 2, 3, and 4 are the tail. And each node has a next variable that points to another node. And you can see this in the code on the right. Class node. We have two things. We have the data that the node is storing, in this case just numbers, 1, 2, 3, and 4. And we have the next node that it points to. And we have a constructor for making a new node out of some data. That's all there is to it. That's going to be our entire linked list in terms of the data structure itself. We still have to implement some operations on it to make it useful, and we'll go through that. But just as an example of how to use this thing, we can set const head equals to node 1 on line 10. This just creates the one node, but we have to set its next to something. So let's set it to another node, new node 2. And let's set node 2's next to node 3. The way we do that is head.next equals node 3. So head is our 1, dot next would be 2, dot next setting it to 3. And same thing with 3 and 4. And we can JSON stringify this and see what it looks like in JavaScript. Well, in JSON, we have at the top level an object containing data, which is just 1. And then next is another object, which has data 2. And a next, which is another object, has data 3. And also a next property, which is data 4. And its next property is undefined, so JSON.stringify doesn't render it. Pretty straightforward. The first thing you want to know, the first operation, is traversing this thing. So we want to get the kth element out of the linked list. Well, you just got to break it down. What are we exactly doing here? We're starting at the head because head is the only thing we have. This dot head that I'm referring to, I wrap this in a class, and the only data member it has is this dot head. That's it. We're just keeping track of the head, and then we want to get to the other nodes. We have to traverse to them. That's the nature of a linked list. If we knew where the nodes were in memory, then that would just be an array. The point of a linked list is that you have to traverse the nodes to get there. But it makes it very efficient to operate at the head because you can just stick one at the front. We'll see that in a minute. So getting the kth element from a linked list. First of all, if the head is undefined, then no matter what k they give us, it's going to be out of range. There's no k that they could possibly provide to us if the head is undefined because there's no data in the list, so there's nothing to get. So we just throw an exception. I'm not a JavaScript developer. I think typically in JavaScript you'd want to throw an actual exception class instead of just throwing a string, but this works for our purposes. The next line of code here, let cur equals this dot head. So we have a new variable cur, and we're starting at this dot head, and cur is going to keep track of where in the list we are. We just need to follow the next reference k times. So we're traversing through the list, going through, decrementing k by 1 each time until we get to 0, and at that point we will know that we're at the node that we want. We could also have kept a separate counter variable and compared it to k, like we count up increment every time, and once it reaches k, we're done. But it's easier to just decrement k. K is copied. This is call by value stuff, so we just decrement k. So while minus k is greater than or equal to 0, well, if we're going to immediately just traverse the next node, right? So if the next node is undefined, if there's nothing there to traverse to, we have to throw an exception. This indicates like we still have something left in k. K is greater than 0, or greater than or equal to 0. So we still have k left to go. And we have run into a cur that next goes undefined. So there's a hanging, there's no more list after this point, but we still have k to go. So we know that the k they've given us is greater than the length of the list. And so in that case, we're out of range. We have to throw an exception. But if we're not out of range, we just go to the next node. And we continue this loop around and around and around until we get to the node that we want, where our decrementing k has reached past 0. And when it passes 0, then we won't evaluate the body of the loop anymore. So k is 0 at this point at line 31. And we know that cur is pointing at exactly, k is -1, but we know at this point on line 31 that cur.data is the data that we want. Cur is the node that we are trying to get to, that we have traversed to. That's all there is to it. We're just traversing through the list one at a time, going cur equals cur.next, cur, cur.next, cur, cur.next, until we run out of k, and then we're at the place we want. Note well though, cur is a node. It's not like an array where we're like, this is the memory index we're interested in. Now we're going to the next memory index. No, we're going from one object to the next object. And that's sort of the mindset you got to be in this case. Cur is a node. All right. So how do we add things? Oh wait, there's one more point here, side point. My nerdy CS brain, who has worked with Scala way too much for my own health, sees this list construction that we've come up with and thinks, this is recursive, isn't it? This list that we have, 1, 2, 3, 4, has a tail, this 2, 3, 4, which is itself a list. 2 is the head of this list, and 3 and 4 is its tail. As a recursive structure, and we can break it down even further. 3 is the head of a list, where 4 is its tail. And even 4 is the head of a list with an empty tail. But since the data structure has a recursive structure, we can write recursive algorithms that are very natural to interact with this thing. Let's take a look at it. Get the kth element from a linked list recursively. So what we're going to do, this text on the left, We're starting at the head because head is the only thing we have. This dot head is the only pointer into this data structure that we have available to us. So we're always going to be starting at the head. Now, the recursive step, the interesting bit, is we're going to get the k minus 1th element from the tail of the list, which is the one that is located at head.next. So we're constantly getting the our recursive implementation is going to be whatever our k is, whatever our list is, we're interested in the k minus 1th element of the tail of that list. And we just keep going until k is 0, and that's our base case. And that's exactly what the code indicates. Supernatural, not supernatural, but it is supernatural to write. We have a helper function inside here to make things a little bit cleaner. Function helper, it takes the head of a list and k. So if the node is undefined, then we've gone out of range. We've overshot, so we can't do anything at that point. They've given us a k that is greater than the list is long. And there's no way to get a node that doesn't exist. So we have to throw an exception. Otherwise, if k has reached 0, this is our base case, and we just return node.data. We return the data in the node. Again, we don't want to expose the node itself. We just expose the data inside of it. If k is still greater than 0, then we just recursively call the helper on the tail of the list with k minus 1. And then our get recursive implementation of get recursive of k is just calling the helper function at the head with k. So we're going to be getting the k minus 1th element out of the tail of the list, getting the k minus 2th element out of the tail of that list, getting a k minus 3rd element out of the tail of that list, and so on until k equals 0. And that's our base case. So we'll return out, we'll return out, we'll return out, we'll return out, we'll return out on line 35. And that's it. Always the rule with recursion is just trust the recursion. You'll get there. This is my side note about thinking about things recursively. And in fact, this is the way that you would do it in a functional programming language. It's always very natural to write recursive code. JavaScript, unfortunately, does not have tail recursion, which means that line 32, when it is returning this reduced problem of finding k minus 1 element of the tail of the list, the problem is getting smaller every time, but you're also adding a stack frame every time. Some languages are smart. Kotlin, Scala, Java even, I think. Functional programming languages usually also have this language feature called tail recursion, which means that it will just replace the stack frame instead of adding a new one. Because we're not doing anything after line 32 inside our function. So we can just call helper and then forget about all this stuff above. I mean, there's no variables there anyway, but it does add a stack frame. So you'll see in a stack trace, for example, that we've got all these function calls that accumulate. And if you're going through thousands of elements, then you'll have a stack trace that's thousands of elements long. And that's not great. Maybe you don't want to write your code this. I'm sorry. Maybe don't want to write your code this way in JavaScript, because you run into this issue. Certainly not in Python or something where the limit on recursion depth is very small. But it's a good way to start thinking recursively. All right, now we'll get to the question of how do we add things to this list. I'm going to start with adding things to the head of the list. It's the easiest case. Operations at the head of the list are linear, are constant time. Of course, they are. It makes sense. You have this diagram, this top line is our list ABCD, and we just want to add a new node to the front. All we're doing is creating a new node that points to A and setting this head to point to the new node. That's all you have to do. It's just 3 lines of code. We keep the old head in our pocket so we know what to set it to, set the new node to. we set the head of the list to our new node and set the next of the head to the old head. So back in our diagram, we are setting the head of the list to this new node, and we set this new node.next equals to A. That's all that you have to do. It's really fast. It's just an object allocation and setting a pointer on the new node to point to the new array, or to the old head, sorry. Compare this at the bottom here to insertion into an array. Say you're going to insert at the head of an array at position 0. At index 0, we have a new element in here, but notice that all these other elements have moved over by 1. We had to shift n elements over in order to accommodate this new one. It's not great. Now, computers are very efficient at shifting in memory. Assuming that the entries are word aligned and everything, which the runtime will take care of for you, usually you can just there's a CPU instruction to just, oh, hey, memory controller, just move this data over by a word or something. And it can do a large block of this array and take care of it all in one memory instruction. And it's very fast. So in practice, JavaScript has push and pop functions on its array that just operate the head of the array. And it's really fast. You can also do optimizations like maybe secretly keeping some extra memory before your array. If you're running the JavaScript runtime, what's it called, like V8 or something, or Spider Monkey in Firefox, or Node. Well, Node uses V8, or whatever it's called now. Didn't it change? I don't know. So you can keep some extra memory back there so that you can, get away with cheating a little and putting new nodes or new data. There's no nodes in an array. It's just data. Putting new data at the front. But in general, yeah, you have to shift the whole array over at some point. And you don't have to do that with linked lists. You just stick a new node at the front. So that's sort of the reason d'etre of linked lists. It's efficient. It's linear. I can say it again. It's constant time instead of linear. And as I just alluded to, this is perfect for stacks. If you're just pushing and popping on a stack, you're only operating at the front of the linked list. You're only pushing new nodes out the front or popping the head of the node off. So these operations at the head are really naturally implemented with linked lists. It is fine to use arrays in JavaScript for that, and that's what people always do. But, linked lists are nice. So the next question, what if we want to insert somewhere in the middle of the array, or at the end or something, instead of just at the head? This is costlier, right? You have to traverse to where you want to go. The only thing that you know to start with is the head. So if you want to insert between C and D, you got to traverse through B to C in order to do that. So this is a big O of N operation. Always in linked lists is linear in the size of the list. But you can do it. You don't want to do it very often, but you can do it. How do we do it? So we in our diagram here, just looking at the diagram to start with, we are creating a new node, and we are setting C.next to the new node, and we're saying new node.next to D. And that takes care of inserting this thing. Because the next time we traverse through, we're going to go A, B, C, and C.next is going to take us to the new node, and then this .next is going to take us to D. So we have effectively inserted this new node into this list just by changing these next pointers. What does this look like in code? It's going to be more complicated than the last example, but it's not too bad. We're going to start off with a special case, just update the head. If k equals 0, if we're trying to insert at the head, then we can just call our insert a head function from the previous slide. We already have it implemented. We're done. And we return. That's the easy case out of the way. Well, there's another easy case on line 51. If the head is undefined, at this point k has to be greater than 0. And we're trying to insert, so we're trying to insert somewhere that is not actually in existence. There's no data in this list if this head is undefined. So if we're trying to insert somewhere that's not k equals 0, then we have a problem. We have to throw an exception. Line 55. Now that these preliminaries are out of the way, we're going to do the same traversal that we did before. We have a cur variable that's keeping track of the node that we're at currently, which is going to start at the head. That's the only thing that we have, once again. We're going to do the same loop as before by looping over cur equals cur.next each time. If we run into an undefined early, then we're out of range. The only difference here from getting the kth element is that we're stopping short. This is minus k greater than or equal to 1 instead of 0. So this is the last time that this line 60 is going to run is when k equals 1 instead of at 0. What this means is that we're stopping one node early before the k that they told us. So in this case, we're inserting at position 3. This is 0, 1, 2, 3. But we want to stop at 2. We're stopping with cur at the k-1 node. We're stopping at the c node because we need to set c.next equal to our new node. So we're stopping one early. If we overshot to d, there's nothing we can do with d. We need to set c.next. So we're saying c.next for our new node, and we also set the new node.next equal to d. That's all we're doing in the last 3 lines there. And we have successfully inserted the new node. Makes sense? Just traverse to where we want to go. Well, we were traversing to 1 before where we want to go. And then we're setting c.next, in this case, to our new node. And we're setting the new node to next to d. We're good. What about removing elements? Once again, we'll start at the head. And this is really easy. This is the easiest one of all. We're removing the head element, or the head node, in this case, which is just a. And the only thing we have to do, the one thing we have to do, is move the head pointer to b. That's it. This.head equals this.head.next. So we're setting head to head.next, which is b. So we're setting the head to b. And now the next time we traverse this list, we're going to be starting at the head, which is now b. So all our offsets work fine if we're getting the kth element, because we're starting at b this time. The only thing to note here is that a is still pointing to b. It's still there. The object still exists in memory. But since the only thing we are keeping track of is the head, there's no way to get to a. It's just sort of floating around there in memory. And since it's part of an unreachable part of the subgraph of the object graph, I guess the subgraph is size 1, it will get picked up by the garbage collector. If we were in a manually memory managed programming language, then we would have to free a to free up that memory so it doesn't sit around forever. But we're in a garbage collected programming language in JavaScript. So we can just, leave it there, and the garbage collector will take care of it eventually. But for us as users, I say users, as programmers using the JavaScript runtime, we don't have to care. We just sort of leave A pointing at B, and we don't care. So yeah, looking at this code, it's very straightforward. Line 69, if this head is undefined, this is trying to remove the head of a list that has no head, which is something that you cannot do. It's like when the slasher tries to cut off Seltie's head in Errata, and the sword just goes through her helmet, and she's already headless. She can't be beheaded. So we throw an exception out of range. And then the only other thing to do is this head equals this head at next. We're good. But you know the next thing I'm going to go to, which is how do we remove a element at the kth position in the list instead of just at the head, right? Let's go into it. To remove the kth element, we traverse to there, and then we do our magic. Once again, we're traversing to the k minus 1th node, which in this case we're removing c, so we traverse to b. And then we change b.next to point all the way across to d, I'm sorry. So b points to d now. And once again, c is still pointing to d. We do not care. There's no way to get to c. Let's look at the code. If we're moving the head, k equals 0, then we just call our function remove at head. If there is no head, then at this point, by line 82, we know that k is greater than 0. And we're trying to remove a list with no head, which means the list is empty. So we're out of range. There is no such element k to remove. So line 86, we do the same thing as before. We have a cur variable that starts at the head. We are traversing, starting one early, or ending one early at this greater than or equal to 1. And if we run into an undefined early while k is still greater than or equal to 1, then we have gone out of range. The list is not long enough to satisfy this method call, so we throw an exception. And we just traverse the cur equals cur next. We're just going through the list to 1 before. And once we arrive at the node that is 1 before where we're interested in this case b, we only have one thing left to do. Cur.next equals cur.next.next. So in this case, it is b.next equals b.next.next. We're starting with our old list here. So b.next equals b.next, which is c, .next, which is d. We're running b to d. That's all line 94 is doing. You just have to think this out. Cur.next.next is like skipping one, right? Note that b.next.next might be undefined. If c is the last element of the list, right? It could be undefined, and that's fine. B will just point to, b.next will just be undefined, which means it's the end of the list now. Cool. We're fine with that. We don't have to check that case separately. We're good. All right. So I've sort of been talking about this as if it's in a class, right? All my head references are this.head. And we'd like to do this. We'd like to wrap this up in a class so that the users don't have to care about nodes and whatnot. They just pass their data into insert and they get their data out of get. And they can remove elements at the kth position. That's the only API you need for a list. Well, these are the three things we have so far. Get the data in the element at the kth position, insert some data in a new element at the kth position, and remove the element at the kth position. But there is sort of one thing missing. You don't need it to use the list, but it's not great to leave it out. Because users all the time are going to be wanting to write code like the code here at the bottom. For a loop from I to n, we're just going to print out the ith element of the list. Or something else. They want to call some function on all the elements of the list, or all the elements that match some predicate, or they're going to want to print, like it is here, there's a million things you could do with all the elements of a list. And you want to just loop through them all. But if they write this code, really the best they can do is this code. It's going to be quadratic. And it's kind of pathetic to have a just linear list data structure that has quadratic operations. Like, if you have 1,000 elements on this list, you don't want to be doing 1,000,000 operations just to print 1,000 elements. So we'd like to provide them with a fourth bullet point, a new method that they can call to somehow get around this quadratic problem. You can see it's quadratic, right? Because list.getI, if you amortize across all the possible i's, this is on average going to be n over 2 traversals to the next node in order to get to the middle element of the list on average. And then the outer loop is going across n times, so it's going to be n times half n, which is half n squared, which is big O of n squared. We don't want this quadratic nastiness in our user's code. So let's give them some option. And this is a perfect application of iterators. Let's take a look. There's a lot going on here because there's a lot of syntax. JavaScript has lots of syntax trivia, and we got to cover this briefly. So the first piece of trivia you need to know, this first bullet point here, is putting the name of a method or of a variable inside square brackets. And I think also it works in object properties. Not 100% sure on that, but I think it does. If you put the name of a method or variable in square brackets, then actually what it will do is evaluate the expression within the square brackets and use that as the name. So I could put like A plus B in here, like in quotes, like the string A plus the string B, and it would have a method named AB. So you can construct method names programmatically by putting them in square brackets. In this case, we're not doing anything fancy. We're just using this variable, this property of symbol, which exists in the JavaScript runtime. Symbol.iterator it evaluates to the name of a magic method. Magic method is just like Python, that we thought we had escaped by not using Python anymore. But they come back to haunt us because JavaScript has one too. It is, well, it has many of them. But in this case, there's a special method which is called like at iterator or something like that usually. But it can be different, I think. Like, I think Node.js might use a different one. I'm not 100% sure about that. But in any case, it's nice to just put the square brackets in and get the perfect name of the method that is always going to be correct, regardless of the runtime. And that's what I've done here. That's also what I've seen conventionally like used around Stack Overflow and whatnot, is people use these square brackets and use symbol.iterator. It does evaluate to a string. That's all I'm trying to get across. Like, putting it in square brackets, having symbol.iterator inside evaluates to some string, which I think is at iterator or something like that. All right, so that's out of the way. We have a method named at iterator, I think, something like that. The next point on the list. Oh yeah, the whole idea of this at iterator function method in this case is that that is the method that gets called when you put it in a for loop like this, a for of loop. So our users can just call this, can just write this code rather. It just looks like for let cur of list. They're just looping over list, and they can console.log cur. This of, like, it just calls this function to get the iterator that it's going to use to implement this first-class language support for each loops. So this is what gets invoked actually when you call this. And of course, arrays and whatnot have this implemented already. But we're designing our own custom data structure, so we've got to implement it ourselves. In order for this to work, in order for us to be able to use this in for of loops, we have to implement the iterable protocol, which is just, it has to be a function that returns certain kind of object that has functions that are defined on it. Fortunately for us, we don't have to know the ins and outs of the iterable protocol because generator functions implement it for us. What are generator functions? That's the last bit of trivia here. Putting a star in front of a method name or function name makes it a generator function. And this is kind of like like async functions in JavaScript. If you have an async in front of your function name, then it will always return a promise. Well, generators, if you have a star in front of your function name, generators will always return a generator. Generator functions will return a generator. And what's nice about generators is that the special keyword that you can use inside them is yield. What yield does is it's just like yield in Python. It returns whatever data this is, cur.data. But the next time the function gets evaluated, it resumes execution with all the same local and like block and function scope variables set to the same things they were before. It resumes on line 111. So we can just write code like this. Starts at the head. As long as we haven't run out of nodes, then we yield the data that's at cur, and then we move cur to cur.next. So the first time this gets evaluated, it will start at the head. It will check that it's not undefined. If the list is empty, then it's not going to yield anything. But if it is defined, then we yield the data that's there. And now the next time we go around this loop here on the right, it will resume execution on line 111 with the same cur that was before, which starts at the head. So we get cur.next now, and we go around the loop again. And it will yield cur.data, which is the next node. And this will come out in the loop, and then it will run this body of this loop. And the next time around, it will resume after the yield again and go around this loop. Kind of funky if you haven't seen generators before, but it's also straightforward. I mean, this code is super simple to write. You're just yielding something. If you're not using generators, what you would have to do is have a like get next method that you just call every time, and has to keep track of some internal state about like where you are in the list, and that would you'd have to close over that data manually. But here you just like it's just a language construct. You just yield, and it automatically saves all your local variables, and then resumes on line 111 the next time it's called. So you don't have to implement like a next function that keeps track of your cur and some variable outside somewhere. We're all good. This is very simple. So it's a perfect application of generators and a perfect demonstration of iterators. You conventionally do always just use a generator when you're implementing the iterable protocol because it's so easy. It's nice that they added that. All right. Let's move on. Reversing a linked list. This is a common interview question. Because if you haven't worked with linked lists before, it can be kind of intimidating. Like we start out with this list, this list on the top right here, this diagram. How do we turn these arrows around to point the other direction? Well, what do we actually want in the end? Well, we want A to be pointing off to undefined, right? A is going to be the new last element of our list. We want B to be pointing to A. We want C to be pointing to B, D to be pointing to C, and E to be pointing to D, and the head variable to be set to E. That's what we want, and that's what this code does. It's going to be a little bit more involved than the previous examples, but you can also follow it. It's not too bad. The key sort of insight that it helps to keep in mind with this is you can keep track of two different variables to track your position in the list. We have a prev and a cur. So we're going to start out, well, as soon as we verify that this head is actually set to something. If the list is empty, then we can just return. We don't have to throw an exception, by the way, because you can reverse an empty list. It's a no op. You don't have to do anything. But say it is defined, so we have something to do here. Let prev equals the head, so we start with prev at the head. We start with cur at the head.next. So we're starting with cur at B, starting prev at A. And we've got these two just set like this, and they're going to march across in unison. Prev is always going to be one before the cur. So while we haven't overshot the end yet, we're just going to go through this whole thing. While cur is not yet undefined, it will get to be undefined at the very end. We're going to set this local variable next equals cur.next. we're going to set cur.next equals prev. So in this case, we're starting, b is going to be our cur to start out with. We're setting b.next equal to prev, which is a. So we're basically turning this red arrow around to point to a. And then we march them across. Prev equals cur and cur equals next. And we just do this across. I can go through all the text on the right here. We just sort of walk through it. Start with prev equals a and cur equals b. We set b.next, we move the red arrow around to point to a. Then we shift them across. Next up is prev equals b, cur equals c. And we set c.next equals to b. So we're moving the yellow arrow across to point to b. We're rotating it around, I guess, to point to b. Next up is prev equals c and cur equals d. We've marched it across one more step. And now we move d.next across to point to c. We also need to do this to e as well. Move e.next across to d. And we're done with the loop, our while loop. And then the last two steps, the only other things we have to do is we still need to set a.next because it's still pointing to b at this point. We just set that to undefined instead because it's the last element of the list now. And we also need to set this.head equals prev, which is going to be e at the very end. Once cur is undefined, like once we've got out of this while loop, cur is now undefined. We have to look at prev at this point. So prev is going to be e at the very end. This.head equals prev. And that sets the head of the list to now be e. That's all there is to it, really. You just have to have that insight of like, oh yeah, I can just keep track of two different elements. It's a little bit trickier to write if you are only keeping track of basically prev. It doesn't read as clearly, but you can do it. And this is also something that it helps just practice by writing. So test your knowledge. It's a little bit brain twisty, but you get the hang of it. All right, here's a problem. What if we're always appending to the end of the list, or frequently appending to the list? Like, for example, if we're implementing a queue, where we're taking elements off one end and appending them to the other end, no matter which end we choose as the head of our list, like we're going to be doing operations at the other end. And this is a problem for us, because we'd have to traverse all n elements every time to get to the end of the list to do operations at the other end of the list. And we don't like our linear time operations, especially when we're competing with arrays, which you know exactly the address in memory you're going to, and you can get there in constant time. So it would be nice if we didn't have to traverse all the way to the end. And our solution is going to be keep a reference to the last element. You know, we have a pointer to the head, a variable that points this.head equals a in this case. Let's keep another one, this.last equals e. So now we know e. We know, we can insert e very easily by just setting e.next to a new node, right? And then moving the last variable to point to our new node. Very easy. But how would we delete the last? If all we know is last, we can look at this screenshot here. We construct a new linked list, A, B, C, D, E. And we're looking at list.last. I've added this to our list implementation. All we have here is a node that has data E and next undefined. That's all we have. So how do we delete E? In fact, we need D. We need a pointer to D so that we can set D.next equals undefined. We don't need E. We don't care about E. We're getting rid of E. We want to set D.next to undefined. But we can't get to D without traversing through the whole list. So we have a problem. We could keep a second to last pointer. This is a bad idea. But then when we delete E, say we delete D now there's no pointer to C. We have to traverse to get there. So we haven't really solved our problem. We could add third to last, and we do this for all the nodes, And now all we have is just basically a big array of pointers into our linked list, and we might as well have just used an array in the first place. Because in order to, insert and delete in this array, we're going to be paying the same costs about like shifting elements over and whatnot. So this isn't a good answer. Let's keep it to just head and last and see what we can do. So we have a head element and a last element, and we'd like to implement some way to delete E. There's a clever idea that we can do, and it's given away by the section title at the top, doubly linked lists. So this is what they look like. It's just a linked list, except we have pointers going in the opposite direction too. So each one has a next and a prev field now. So the next of A is B and the previous is undefined. The B node has next equals C and previous is A, and so on. At the last one, next is undefined and previous is D. And we also have this new this.last field, which will always let us get directly to the last element. Now, to delete any node, we just set node.prev.next equals node.next. Make sure that makes sense. So say we're deleting D. We set d.prev, which is c.next. So we're setting c.next. We're moving this arrow to point to node.next, which is E. So we're setting c.next equal to E. Node.prev.next equals node.next. We're drawing that arrow around the E. And that's all you have to do. It works for the last element too. If we're deleting E, e.prev.next equals undefined, which is e.next is undefined. We don't have to special case that. It just works. The only thing it doesn't work on is A, the head of the list. So you have to have a special case for that because there's no a.prev. But you can just write a line of code for that. It's fine. Easy. Yeah, that's it. There's another lecture on hashing, but it'll be a separate video. All right. Hope that helped.